Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.2. The limit of a function.
Lesson 1. The concept of a limit. Today we're going to talk about the limit of a function. And as a quick review, I want to remind you how to find the output of a function, not from the equation, but from the graph of the function. So here we have a function, y equals f of x, that's been graphed. And I have several inputs down here along the x-axis. The first thing I want us to do is to find f of 3, the output of this function when the input is 3. Well, how do we do that from the graph? Remember that 3 is the input, so here's our input. And to get the output, we simply go from the input vertically and draw a vertical line until we hit the black graph, and then we go over to the y-axis because those are the outputs. And notice that I hit the value 8 on the y-axis. And so f of 3 is equal to 8. When I put an input of 3 in, I get an output of 8. Let's try a few others. If I want f of 5, that means that my input value is now 5. To get the output from the graph, I simply go up to the black graph. Wherever I hit it, I go horizontally over to the y-axis. When my input x is 5, my output value y is equal to 4. And so I go ahead and say f of 5 would be equal to 4. Sounds simple, right? Now let's go to 8. I want f of 8, so my input value is 8. To get the output value, I draw a vertical line. I go up until I hit the graph. But what happens in this case? I try to hit the black graph, but I've just hit this circle. And remember that a circle is just a point that's missing on the graph. So when I try to hit the graph, I don't hit it at all. I go right through it. That circle means that there's a point missing. And so there is no output value associated with the input value x equals 8. I simply go right through the graph. And so we would have to say that f of 8 has no value, or we simply say that the function is undefined. So when I try to put x equal 8 in, I can't find a corresponding y value, and so f of 8 is undefined. Let's try 10. Does the same thing happen here? I can see there's a circle on the graph. Well, I put the input value 10 in, and I go up until I hit the black graph. And notice in this case, there's a solid dot here. Well, what does a solid dot mean? That's where the graph is. And so I go up until I hit the solid dot, and I go over to the y-axis. And notice I get an output value of y equals 4 again. So f of 10 is equal to 4. Okay, why don't you try the last one and see if you can decide what f of 12 would be. Okay, f of 12 means my input value is 12. So I start on the x-axis at 12, and I go up until I hit my graph. And notice that I hit the graph right here at this solid dot. I don't go up to this portion of the graph because I've already hit a black dot right here. And so when I put 12 into this graph, I go up to the black dot, then I go over horizontally to see what the corresponding y value is. And notice that I happen to get 4 again. And so f of 12 would be equal to 4 for this particular function. All right, we've talked about finding inputs and outputs from the graph. Now I want to start into a discussion that's going to lead us to the definition of what we mean by the limit of a function. Well, let's look at this example that's right here. I have a rather complicated looking function. F of x is equal to x cubed minus x squared minus 2x, that whole thing divided by x minus 2. Well, I want to ask a question before we start thinking about inputs and outputs for this function. What is the domain of this function? What x's am I allowed to plug in? It's a rational function, and remember that means that we have one polynomial in the top divided by another polynomial in the bottom. And for a rational function, remember that its domain is all x's for which the denominator is not equal to 0. So what we would have to worry about is when this denominator, x minus 2, would be equal to 0. And what value of x does that happen for? It happens for x equals 2. So if I plug 2 into this function, I'll get something in the top. I will get 2 minus 2 in the bottom, which means I get 0 in the bottom, and this rational function would be undefined. So the domain is all x's except 2. If I plug in anything else, I'm okay. So I'm going to say that the domain is all real numbers x, we often say just all real x, not equal to 2. Any other value will give me something non-zero in the denominator, and so my function will be defined. So let's think about that. We cannot put 2 into this function, but we can put in any other number, and we can put in numbers that are very close to 2. 2 is the only real number I'm not allowed to put in. Let's look at this little table that I have here over on the left. I have a bunch of x values listed, and let's write down what the output values are. For example, when x equals 1, I'd plug 1 in for x, and I do 1 cubed minus 1 squared minus 2 times 1 divided by 1 minus 2. If you were to figure that out, let's see, we would have 1 cubed is 1, minus 1 squared is 1, minus 2 times 1 is 2, and I'd be dividing that whole thing by 1 minus 2. Well, I've kind of squished that in there, but if we calculate it, let's see, I'll get negative 2 in the numerator divided by negative 1 in the denominator, and I get an output value of positive 2. If I want to put 1.5 in for x, remember that's okay. That's not the value 2. That's the only value I'm not allowed to plug in. So I'd replace all the x's with 1.5. Well, I don't want to do that longhand, so I did it on a calculator. And when I plugged 1.5 in for x, I got the value 3.75 for the output. So f of 1.5 is 3.75. How about 1.9? Is it okay to put that value in? Well, we can put in anything except for 2, and 1.9 is not equal to 2. So I went ahead and replaced all the x's with a 1.9, and I ended up with an output value of 5.51. I did the same thing for 1.99. It's very close to 2, but it is not equal to 2. And when I plugged that into my calculator, I got 5.9501. I did the same for 1.999. Again, that's okay, it's not equal to 2. And I got the output value of 5.99501. I'm going to ask this question. What's happening to the x values? I had 1, 1.5, 1.9, 1.99, 1.999. Those are getting closer and closer to the value x equal 2, that forbidden value where a function is not defined. Now, I want you to concentrate on the output values. Our output values were 2, 3.75, 5.51, 5.9501, and 5.995001. Are those values getting closer and closer to some number? It appears as if these output values are getting closer and closer to 6. We haven't proved that, but it certainly looks like as the input values get closer and closer to 2, the output values are getting closer and closer to 6. So as the inputs get closer and closer to 2, the output values get closer and closer to 6. And what we say then is that the limiting value of this function, as x gets closer and closer to 2 through values that are a little bit less than 2, the output values are getting closer and closer to 6. We say the limit of the function is 6. Notice that the same thing happens if I put in x values that get closer and closer to 2, but through values that are a little bit larger than 2 instead of values that are a little bit smaller than 2. When I put 3 into this function, I get 12 as an output on my calculator. When I replace x with 2.5, it turns out that I get 8.75 as an output. When I put in 2.1, I get 6.51. When I put 2.01, a number very close to 2, but again not equal to 2, I get 6.0501. And when I put in 2.001, I get 6.005001. These x values are getting closer and closer to 2 through values that are a little bit larger than 2 in this case. And notice that the output values are again getting closer and closer to 6. So whether our inputs get close to 2 through values that are a little bit less than 2 or through values that are a little bit greater than 2, in both cases the outputs are approaching 6. And we say in words then that the limit of this function f of x as x approaches or gets closer and closer to 2 is 6. The limiting value of this function is 6. And we even have a nice way of writing this. So let's go to the next slide and see how we would write that. Let's try to fill in this blank. We call 6 the blank of f of x as x gets closer and closer to 2. So we talked about that on the last slide. We say that 6 is what is referred to as the limit. It's kind of like a speed limit when you're driving a car. If the speed limit is 50 miles per hour, you can get very close to that limit. You're not allowed to go over that limit. So we call 6 the limit of f of x as x gets closer and closer to 2. More formally, and this is just the formal way that we say the limit of f of x as x approaches the number 2. That limit is 6. And we have a special notation for that as well. We write it this way. We don't like to write that whole sentence out, so we have a shorthand for it. We write LIM for limit. We write f of x, that's our function. And below the limit symbol, we write an x, and we put a little arrow, which just means it's approaching, and the number that x is approaching is 2. So this portion of our writing says the limit as x approaches 2 of f of x becomes our equal sign, and that limit is equal to 6. And we can read it exactly the way that these words are read. The limit of f of x as x approaches 2 is or is equal to the number 6. All right, now what I'd like us to do is look at this limiting process graphically. We found the limit of 6 from a table. At least we guessed that the limit was 6 because it looked like the outputs were getting closer and closer to 6. But let's go back and see how that would look in terms of the graph of this function. So we're going to try to graph x cubed minus x squared minus 2x all divided by x minus 2. That looks awfully hard to graph. It looks very complicated. Why don't we try to simplify this a little bit before we graph it? We'll try to simplify the expression for the function. Remember though, when we go to the graph, that the domain of this function is all real x's that are not equal to 2. That is the one value that I'm not allowed to plug in. And so when I go to the graph of my function, I should not have an output value associated with the input value x equal 2. Just keep that in the back of your mind. Well, how would I go about simplifying this? One way to do it would be to try to factor. Let's see if this thing factors. And I'm going to try to factor the top. I notice there's a common factor of x, so let me pull that out. So I'll pull an x out. I'd be left with an x squared minus x minus 2, and that whole thing is divided by x minus 2. Not much I can do to factor the bottom, so I'm just going to put parentheses around x minus 2 in the bottom. In the top, this quadratic expression here may be factorable. So let's see if we can factor it. And I'm going to try to factor it into two binomials. And if I can, perhaps I can simplify this function. So let's see. We're factoring x squared minus x minus 2. I need an x and an x. To get a negative 2, I'd have to have a 1 times 2 and opposite signs. Let's see, I want a negative 1 for the coefficient of the middle term. So what do I need? I think I need a negative 2 and a positive 1. And yeah, if I FOIL that out, x squared, I have a negative 2x, a positive 1x. That does give me negative x, and negative 2 times 1 is negative 2. Well, what do you notice here? Notice that there's a common factor of x minus 2 in the top and in the bottom of my expression. So I can go ahead and cancel those. Now, ordinarily in algebra, we're a little bit sloppy and we just say, oh, those cancel out, and I'm left with x times the quantity x plus 1. In calculus, we're a little bit more picky, a little more careful, because remember, you can only cancel a like factor in the top and the bottom if that like factor is non-zero. So as long as x is not equal to 2, as long as it's in our domain, then x minus 2 will be a non-zero factor, and it's okay to cancel those two. So as long as we exclude x equal 2, I can cancel those, and I can say that my original function f of x is the same as this function x times x plus 1. And remember, we're keeping in mind that that's for the values x not equal to 2. All right, let me go ahead and just multiply that out. That'd be x squared plus x. So I get f of x is the same thing as x squared plus x, as long as we add this little condition that x cannot be equal to 2. Remember, for these two expressions, the original complicated one that we had and the x squared plus x to be the same function, they have to have the same rule, but they also have to have the same domain. So we have to artificially add this condition that we can't allow x to equal 2 so that the domain of this function matches the domain of the function we were given. Okay, great. So let me write this instead of f of x as y, because that's just easier for graphing purposes. And so I get y equals x squared plus x. Well, what kind of graph would this be? It's a quadratic function, and so the graph will be a parabola. And if you want to, you can use different ways, like completing the square or using the formula x equals minus b over 2a to figure out where the vertex is. But it turns out that the vertex of this parabola is at negative 1/2, comma, negative 1/4. So it's going to be a parabola. Maybe I should write that in there. Parabola. Its vertex is negative 1/2, negative 1/4, and it will be a parabola that opens upwards. So let me draw that on my graph. Let's see, negative 1/2, I go back 1/2 unit, and down 1/4 of a unit would be right about here, and it opens upwards. In fact, from the factored form up here, I can see that it will have an intercept wherever f of x is equal to 0. So that would be wherever one of these factors is equal to 0. That would be at x equals 0. That'll be one of the x-intercepts. And at x equal negative 1, that would make this other factor 0. So that's actually the other intercept. And so my graph will end up looking something like this. Let's see, when I put in 1 to this, I get 2 as an output. Let me put a couple more points on. And when I put in negative 2, I actually get, that's a little off of my graph, I get 2 as an output value. So our function is going to look something like this. I believe that is roughly right. If I were to put 2 into this function, of course I'm not allowed to put in 2, but if I put it in to this simplified function, I would get 6. So that would be right about here. So if I graph this without that condition, that x cannot be equal to 2, I would get a parabola that looks roughly like this. However, we have to include the fact that x is not allowed to equal 2 in this case. So x is not allowed to equal 2. How am I going to show that on this graph? This shows that when I put 2 into this function, it does have an output value, and it actually has an output value of 6. And I want to show that this function is undefined at 2. Well, remember what the graph looked like on the last slide where a function had no output value for a particular input value. We denoted that by putting a little open circle, meaning a point was missing on the graph. So if I were to go up to this graph, right at the point where it would hit the graph, I want to actually put a little open circle. So let me go ahead and do that. And that way, if I try to put 2 into this graph, you notice that we go right through the graph and there would be no output value associated with 2. So here's my graph. And what I want us to do now is just to go ahead and try to think about how to find that limit of 6 that we talked about as x gets closer and closer to this input value of 2. But I want us to do it from the graph instead of doing it from a table of values. So that is what we will do next. Okay, so what I want us to do next is to go ahead and see if we can find this same limit that we found from the table, but now by using the graph. Well, how are we going to do that? Remember that we are interested in finding the limit as x gets close to 2 of f of x. So here's the value x equal 2 on the x-axis. And what I'm going to do is the same thing that I did with the table. I'm going to choose x values that are a little bit less than 2. On our table, the first thing we chose was x equal 1. Well, how do we get the output from the graph? Remember that we reviewed that earlier. We go ahead and plug in the value 1 by drawing a vertical line up until we hit our graph and then going over to the y-axis, and we get an output value of 2. In other words, f of 1 for this particular function is equal to 2. Then we chose a value that was a little bit closer to 2. We chose the value 1.5. When I plug that x value in, I go up to the graph, I go over to the y-axis, and we got the output value 3.75. We plugged in the value 1.9, which is very close to 2. We went up to our graph, over to the y-axis, and we got the value in the table 5.51. Of course, it's a little harder on the graph to be quite as accurate as we were in our table, but that's what it would look like graphically. Every time I choose a value that's a little bit closer to 2, you notice that when I go up, I have to go a little higher on this graph and go over to the y-axis, and it looks like these y values are marching up and getting closer and closer to the number 6 on the y-axis. The y's are collecting around the value 6. We can do the same thing for values that are a little bit larger than 2. So we could plug in something like 2.1. That might be right here on the x-axis. I go up to the graph, over to the y-axis, and I get an output value of 6.51. If I plug in 2.01, something even closer to 2, when I go up to the graph and over, I get something that is clearly closer to 6 on the y-axis. In this case, I get the value 6.0501. The closer I choose my value to 2, but slightly larger, in the graphing terms, slightly to the right of 2, the closer my output values get, my y values collect towards 6. So as the x values get closer and closer to 2 on the graph from both the left side, values less than 2, and the right side, values greater than 2, the closer my output values get to the number 6 on the y-axis. Sometimes we say that the y values are collecting around the number 6. They are collecting around that one single number 6 on the y-axis. So I added something to our little limit symbol here because we are looking at the limit as x gets close to but never quite equal to 2. Remember that if we tried to plug 2 itself into this function, it has a hole in the graph right here. 2 was the one number that we were not allowed to plug in. If I tried to plug 2 itself into this function, I would go right through this hole, and this function is undefined at the value 2. So although it's not a part of the official symbol, oftentimes we write this limit symbol this way, or I write it this way just to remind myself. We are finding the limit as x approaches but is never quite equal to 2 of the function f of x, and that limiting value is 6. That's the value that f of x is getting closer and closer to. And that turns out to be a rather important central concept of the limit, and we'll talk about that more in our next example. Okay, let's go ahead and go to the next page. And here we're just going to write down our definition in more general terms instead of for a specific example. So you notice that I have a graph over here, and that's this black graph of the function y equals f of x. And what I'm going to do is exactly what we did in the last example, but in a little bit more general setting. I'm going to let my x values get closer and closer to some general number a. So if I allow in this picture my x's to get close to a from values that are a little bit less than a, on the x-axis that would be a value that's slightly to the left of a, I could find the corresponding output by going up to the black graph and going over to the y-axis, and that will give me the output value for that particular x input value. So I get some f of x. If I choose an x value that's a little bit closer to a, what does it look like the outputs are getting closer to, if anything? It appears that the closer my input is to the value a, the closer my outputs are collecting to the value L on the y-axis. These were values that were a little bit less than a. Does the same thing happen if I choose a value that's a little bit larger than a? Well, if I chose an x value that was over here and went up to the black graph and over, I will hit some f of x value right here on the y-axis. And the closer I choose my input to a, the closer it appears my output f of x is getting to this same number L. So as my inputs get closer and closer to a, it appears for this particular function that my outputs are getting closer and closer to the single number L on the y-axis. How would I write that if I wanted to write it in symbols? We would say the limit as x approaches a of f of x is equal to, that's the number that they are collecting closer and closer to. So we say the limit is or is equal to the number L. And remember that if you want to, you can add that little not equal symbol underneath the arrow. That's not an official part of the symbol, but it reminds me that I'm looking at the limit as x approaches but is never quite equal to a of f of x. And as x gets close to but never quite equal to a, the outputs are equal to L. So we would go ahead and say this limit is equal to L provided, and let's kind of write it out in words down here. We would say that this limit as x approaches a of f of x equals L provided x gets closer and closer to a single number, and remember the outputs y or f of x are getting closer and closer to the number L in our picture as x gets closer and closer to the number a. And notice in parentheses that I wrote but never quite blank to a. And remember, we said that we're letting x get close to, but never quite equal to a. And that actually turns out to be the powerful underlying concept to the limit. So it may seem unimportant to you as you're first learning this idea, but as we continue on, you'll see that the power of our definition of the limit lies in this fact that we are allowing x to get close to, but never actually equal to a. We're never plugging a itself into the function. And remember in our last example, when x was getting closer and closer to 2, we actually could not plug 2 itself into our function. It was undefined at 2. But that had no bearing on the fact that the limit in that example was equal to 6. Now there is a slightly more formal definition of limit. And let me go ahead and write this out. And in a later section in your textbook, they do discuss the precise definition of limit, which is rather technical and rather complicated, and we are not going to cover that in this particular video. But let's go ahead and read through this slightly more formal definition. We write the limit as x approaches a of f of x is equal to L, and we say in words the limit of f of x as x approaches a is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a on either side, but not equal to a. And what does that really mean? We say the values of f of x can be made arbitrarily close to L. That simply means that if someone comes along and says, well, I want you to be, say, within 1 unit of L, 1 unit above or below, I can go ahead and get the outputs to be within that region by choosing the inputs sufficiently close to A. And informally, we simply say that we can get as close as we want to L by simply making our inputs as close as we need to A, by taking the input sufficiently close to A. If we can always do that, no matter how close someone demands we get our outputs to L, we can make them that close to L by choosing our inputs sufficiently close to A. Then we say the limit as x approaches A of f of x is equal to L. But that more precise definition is discussed in much more detail in a separate section. We are going to generally depend on this more informal way of thinking about limits for this particular video. Okay, let's go ahead and see if we can consider the next slide. Take that one away and put on the next slide. And this next example is going to try to emphasize that idea that for a limit, we do not care what happens at x equal a, only what happens as x gets close to a. So let's go ahead and try to fill in this first blank. When finding a limit as x approaches a, and I have 2 blanks here, blank, blank, what happens at a? And remember what we said is that we don't even care what happens at x equal a when we're trying to find a limit. We don't care what happens at x equal a. We only care what happens as x approaches a. Well, let's see how that plays out in the following example. Each of these parts, A, B, and C, really does represent a slightly different function. These functions were meant to be drawn to look identical, except at the value x equal 10. That's the only place that they differ. And in this particular case, we're going to be asked to find the limit of each function as x approaches 10. Let's look at the example A. For this particular example, as x gets closer and closer to 10, we are going to ask, do the outputs collect around a single number on the y-axis? Well, let's try it. I'm going to put in a value that's a little bit less than 10 to the left of 10. That's my input value. I go up to the black graph, go over to the y-axis, and I get some output value, f of x. As my inputs get closer to 10, what do the outputs get closer to? That's right. They look as if they are collecting around the number 4. Is the same thing true if I pick values that are a little bit to the right of 10? If I choose this input value x here, I can get my pen to write, and go up to the black graph and over, I hit some output value on the y-axis, and the closer that x is to 10, it does appear that the outputs are collecting, sort of marching downwards in this case, and getting closer and closer to the number 4. So if we wanted to fill this out, we would go ahead and say the limit as x approaches 10 of f of x is equal to the number 4. As x gets closer and closer to 10 from both the right and the left side, but never quite equal to 10, the f of x values are getting closer and closer to this number 4. So we say the limit is or is equal to 4. Now, just kind of on the side for our information, I'm going to ask you a little question here. I'm going to ask you, well, what would happen if I actually allowed myself to plug 10 into this function? That should have no bearing on the limit, because we don't care what happens at x equal 10. We only care what happens as x gets close to 10. But just sort of for our information, and I'm going to kind of put this over here in brackets, if I were to plug 10 into this function, notice that if I tried to find the output value, I would go right through this open hole here, and there is no output value. My function is undefined at x equal 10. So f of 10 in this case is actually undefined, but that has no bearing on what the limit is. So I'll say it has no bearing on our limit. It doesn't affect the limit at all, because for the limit, all we do is we allow x to get close to, but never quite equal to 10. And we are completely unconcerned with what happens when x equals 10. In this case, the function happens to be undefined. Let's go ahead and look at this function that's drawn in part B. It is meant to be drawn so it looks identical to the function in part A, except that at x equal 10 we have a solid dot corresponding to the 10 value. If we were to find the limit as x approaches 10 of f of x, we would do it in exactly the same way. We would choose values that are a little bit less than 10, and you notice the closer my inputs get to 10, the closer the outputs get to the number 4 again. We would choose values that are a little bit greater than 10, and the closer my inputs are to 10, but slightly to the right, greater than 10, the closer these outputs again appear to be getting to 4. So the limit would not change at all. Remember, the limit, we only allow x to approach but never quite equal 10, and the limit of our function f of x would still be equal to the number 4. The outputs are still getting closer and closer to the single number 4 on the y-axis. If I were to ask you, what is f of 10? Well, in this case, if I plug 10 into this function, I go up vertically until I hit the black graph. This isn't the graph, this is a hole in the graph, an infinitesimally small point that is missing. So I go right through that, but then I do get to this black dot that is right here. And so I would go over to the y-axis right at that point, and you notice I would get an output value of 8. In other words, f of the number 10 is equal to 8. But that has no bearing at all on the limit of our function. The limit, again, only depends on what happens as the x's get close to 10, but we don't care what happens at that a value, at the value x equal 10. So the fact that f of 10 is defined in this case and is equal to 8 has no bearing on our limit. The limit is still equal to 4, because when we get close to 10, the outputs are getting close to the number 4. Okay, let's look at the function that's graphed down here in part C, you notice nothing weird happens at 10 in this case. It's a curve that just goes right through 10. We say that the curve is continuous right through the number 10. And if I were to choose values that are less than 10, go up to my graph and over, it again looks as if my inputs get closer and closer to 10, the outputs are getting closer and closer to 4. If I choose values larger than 10, go up to the graph and over to the y-axis, the closer my inputs get to 10, the closer my outputs get to the number 4. And so once again, we would say that the limit as x gets close to, but never quite equal to 10, of f of x, that number that the outputs f of x are getting closer and closer to is 4. And so we say the limit of f of x is 4. Now if I were to ask you again, what is f of 10? So again, this is just sort of an extra question on the side. Well, to find f of 10, I would plug 10 into the graph, into my function, by going up vertically to the graph. I hit the graph right here at this point. I go over to the y-axis, and I happen to get the output value 4. So f of 10 is defined, and the output value is equal to 4. That happens to be the same as the limit, but it really has nothing to do with what the limit is. We saw in the earlier examples that f of 10 was 8, but the limit was still 4. And in this very first example, f of 10 was even undefined, and that had no bearing on the limit. The limit was 4. So the fact that f of 10 equals 4, and that happens to be the same number as our limit, really is just a coincidence. It has no bearing on our limit. And that's what we said right at the beginning of this page. When finding a limit as x approaches a is 10 in this case, we don't care what happens at our a value. We don't care what happens at 10. In the first example, the function was undefined at 10. The second example, the function had a completely different value from the limit. The function value was 8. And in the last example, f of 10 was equal to 4. None of those things had any bearing on the limit. In each case, the limit was equal to the same number 4, even though something completely different happened at x equal 10. Okay, let's go ahead and look at the next page.